Yeah, Arjun, is it streaming on YouTube and is the audio fine there? Can you just ensure? Or Ashir, somebody, can you just check it? No, right now it must have started. Just reload it. Is the audio fine on YouTube? You can YouTube on YouTube also? What does that mean? I don't know. Okay, cool. Hello. Okay, can people on YouTube listen now? Oh my god. People on YouTube, Giraffe Math Coder. Can you hear? Can you hear me? People. Okay, somebody just go to YouTube and check, please. Then I can finally start with the class. We are 15 minutes late today too. Oh my god. Why does this happen every day? Okay, cool. Now we will finally get started with the class. So, as I was saying, last day I taught you how to think about problems using extremal principle and how to think in a greedy algorithmic way. And if that algorithm has a monovariant or something, then you find it. Otherwise, you don't. But you don't think from the beginning, um, you know, about induction or about using uh, taking the maximum or anything. You just go along with the flow. You be greedy, and then if it works, it's good. Otherwise, you try global approaches, etc. So all the problems today, they are going to be based on greedy algorithm and extremal principle. So have you guys tried problem one? Because problem one is the easiest. It's kind of like a warm up problem. Problem two, three, and four are considerably harder. So okay, two is also quite easy, but okay, it's actually in the order of difficulty. So one is very easy, two is okay, three is difficult, four is very difficult for your level. So four is in fact an IMO P5, I think. Problem three is from IMO shortlist. Problem two I don't remember. Problem one is from Arthur Angel exercises. But yeah, problem two is also from some other books exercise. But I don't remember which. Yeah. So let's start with problem one. What did you guys think about problem one? So problem one, what does basically say? It says that there is an n cross n chessboard. Oh my, this chessboard doesn't look like one at all. So yeah. There's a n cross n chessboard. You have some rows and you have some columns. Yeah. So the thing is that it says that in every row and every column, like if you take this row and this column in total, then it has n rooks in it. Yeah, says that if if ij is free, that means if this row, if suppose this box is free, that means it doesn't have a rook on it, then in this row and in this column there will be in total at least n rooks. And we have been asked to prove that in total, like in the board, there are greater than equal to n square by 2 rooks. So how do you do this? If you have more than n rooks in the nth row and nth column combined, okay, um, okay, if you do, then what? Then remove any random one of those. I don't know what you're saying, but yeah. Okay, that doesn't make any sense to me what you're saying, but yeah. Try to frame it again. You remove jth column and nth column rook. How do you know there is a, like for any j comma n, how do you know like there is a rook there? There may not be, right? So the condition says if a box is empty, then in that row and in that column there is a total of n rooks. N or at least n. I think at least n. But yeah. Yeah, at least n. Choose any random free square. Okay, choose any random free square, and then what? Do what? Ith row, choose any random free square, and then remove a rook, and then what? Like you removed one rook. What do you get out of it? How can you repeat this? Like once you remove one rook, this condition may no longer be true. That this if there is a free square, then it has n rooks in total. So yeah, don't try to think of this algorithmically. This is like a really, it's like a warm up problem. So I'll just give you a hint. You just need extremal principle for this. So try to think of, maximum, minimum, something like that. Ashir, you haven't failed me. Yeah, that's right. So try to think. So we want free squares. If you have free squares somewhere, then you know that there are some rooks in that row or in that column, right? So if in some row, if you say you have a lot of free squares, then you can say that in the squares that are free in the column, there are many rooks, because this row has a lot of free squares, and uh, these number of free squares will also be a lot, right? And the number of occupied squares, if you take, that will be very less. So, so how do you do this? So you want lots of free squares, right? You want a row with lots of free squares. So let's just choose the row or column. Choose the row slash column with the maximum number of free squares. That is, with the least number of rooks. With least number of rooks. Cool. Now in that square, so suppose that's a row. Without loss of generality, it's a row. You have some free squares. So suppose this row has k rooks, and k is the minimum, right? So in the squares that the rooks are there, suppose there is a rook here. Yeah. I don't know how do you draw a rook, something like this. But yeah. So if you have a rook here, if you have a rook in this column, as k is the minimum thing, in this column you have at least k rooks, right? So you have k squares like this with rooks, and as this is the minimum, this is the row with the minimum number of rooks. Every other row and column has at least k rooks. So in these columns where you have the rooks, let me just write R for rooks, okay? R, have the rooks. So there are k columns like this, and each has at least k rooks. So we have at least k square rooks there. Cool. And the squares which are free, suppose this is a free square, then this row has k rooks in total, so this column must have at least n minus k rooks, right? So if and how many free squares are there? N minus k, right? So this has n minus k. So n minus k squares in total. Each of those squares in the column, there are at least n minus k square rooks. So if you add all the rooks, there are at least this many rooks. Number of rooks is greater than equal to k square plus n minus k square. And now how do we want to prove that this is greater than equal to n by 2 square, which is like really easy, right? Okay, why k square, Ashir asks. Well, look at the columns, look at the boxes in this row which has rooks. How many such boxes are there? K such boxes are there. We assumed that. And each of the columns with these boxes, these must have at least k rooks. Because if this is less than k rooks, then we would have chosen this column, right? We have chosen the row or column with the least number of rooks. So the squares which are free, we are using our condition on that. The squares which are not free, which have rooks, we are using the extremal principle assumption there. Okay? N minus k squared, because the squares which are free. So suppose this square is free. our problem, it was given that this row plus this column has at least n rooks. Cool? And in this row we have exactly k rooks. So this must have at least n minus k rooks in those columns. And there are n minus k of such squares. So n minus k whole squared. And by quadratic mean, arithmetic mean inequality, this is greater than equal to n minus k plus k by 2 whole squared. Yeah, which is n squared by 2. This is by qm am. It's n squared by 2 actually. Okay, it's 2 times this. Yeah. It's 2 times. But yeah, anyways, it doesn't matter. Like this is the arithmetic mean, and if you take 2 here and take the square root, that's a quadratic mean. So anyways. Huh. So problem 1 is done. Problem 1 is done. Let's try problem 2 now. Okay, for hints for all the problem is just be greedy. Okay, this is the universal hint. How do you control Z here? Undo. Is there an undo button? I don't think so. So I have to cross this. Yeah. Arjun says he thinks the result of P2 is also true if we change 2n by 3 to n by 3 plus 1. Let me check that. Subsets of size 3 prove that each one can be. No. That's not true. That's not true, Arjun. N by 3 plus 1, it's not true. I can give you a construction if you want. Like these subsets are not disjoint, if that's what you are thinking, Arjun. These subsets may have elements in common. You're probably missing that. These subsets are not disjoint. You're probably thinking that these subsets are just disjoint and then doing something with it, right? To get n by 3 plus 1. Okay, so let's take, I don't know, let's take n equals 6. Okay, so 1 to 6 is the set. And I'll tell you the 6 sets and you tell me how you partition them. Okay, so A1 is, let's say, 1, 2, 3. A2 is, let's say, 4, 5, 6. By the way, what's 2 times 6 by 3? That's just 4, right? I say 4 and you say what? You say n by 3 plus 1, which is 6 by 2 plus 1. You say 3. You say you can color 3 elements. I say you have to color 4 elements. Okay, A1 and A2 are these. A3 I choose to be, let's say, 1, 2 and 4. And A4, let's say I choose to be 3, 5 and 6. Okay. A5, let's say I choose 1 and 5, 6. And A6, let's say I choose 3, 2, 3, 4. Cool? Yeah. Arjun says color 2, 3 and 5. Okay, 2, 3, 5, 2, 3, 5, 2, 3, 5 works. 2, 3, 5 works. So, yeah, this coloring will not work then. This sets is not working. Okay, 1, 2, 3 you have, 4, 5, 6. Cool, cool. 1, 2, 4. Okay, among 1, 2, 3 you have to choose at least one. Among 4, 5, 6 also you have to choose at least one. From the first two I guaranteed this. From the third I am guaranteeing that you have to choose. Choosing 4 is not good. Choosing 4 is not good. 1 is there in what? How many? 3. And okay, let me just try another thing. We have 1, 2, and so on up to 6. And you are saying, okay, I have to choose 6 sets such that you can't color with 3. Uh, so A1 I said 1, 2, 3. A2 I said 4, 5, 6. A3 I want 1, 4, or 5. A4, let's say 2, 4, and 6. A5, let's say we have A5, let's say we have 1, 2, 3, 4, 6. So if you right now, if you choose 1 and 4, you are basically done. So I don't want you to choose 1, 4. So let's give them 3, 5, and 2, let's say. Okay, now what colors do you need? Minimum you need to choose. You can choose 1 and 4 and 2, 3, 5, whatever. Let's choose. Let's choose 2, 3, 6. Yeah. Guys, what are the 3 elements that you choose here? Oh my god, I have put 2 in so many. Let's just make this 5, okay? Okay, now I have put 5 in 4 places. So let's see, I'm choosing how many elements in total? 3 times 6, which is 18. Each one must come 3 times. Now 2, 5 works, right? Yeah, yeah. Now 1 and something else will work, probably. If you just take 1 and 2, 1 and 2, and 5, that works. 1, 2, 5 works. Okay, this is a difference of only 1, but if we take n to be big, I am very sure that this will not happen, okay? So let's take n to be very big. Let's take n to be, I don't know. Let's just take n to be 7 and see. 2 times 7 by 3 will be like 2. No. What was my this thing? How many colors do you need? 2 times 6 by 3. 2 times 7 by 3 will be 4. So you need 4 and you are saying n by 3. N by 3 is, okay, you said floor, right? So that will still be 3. So Arjun is saying that he can do it in 3 colors if we take n into n equals 7. So let's try this. We have 1, 2, 3, 4, 5, 6, 7. And let's choose 1, 2, 3. And okay, what about this construction? Okay, this construction won't work. It's stupid. But yeah. Okay, why choose n equals 8? Why stop at n equals 7? Let's just choose n equals 8. So n equals 8, I think I can do it with 2 times 8 is 16 by 3, which is like 5 things. And you say you can do it by 8 by 3, which is like 2 plus 1. So 3 things. So if you pick every third element, 1, 2, 3. I choose 1, 2, 3, 4, 5, 6, 7, 8, 1, and then and 1, 2, 3, 4, 5, 6, 7, 8, 1. Then let's choose 2, 3, 2, 3, 4, and so right now you need one from this, one from this, and one of 7, 8. You need. Because if you choose one for this, okay, already you need at least 3 elements for this. Already you need at least 3 elements for this, and okay, no, you can just choose 4 to bypass that. So let's just make this 2, 4, and 7. 2, 7, 4. Okay, still you can choose 4 and get away with it. Make this 5, 3, and 8. Now you need at least 3 elements from here, and then you just need 1, 1, 2, 3, 4, 5 sets I've chosen. I need 2 more. So right now you have 1, 2, 3, 4, 5, 6, 7, 8, 1. Okay, right now what can you do? You can just choose 1, 4, and 5 you can choose, for example. Right? Or something like that. Okay, yeah. So right now I'll pair 2 with this thing. 2 I previously paired with 7, so I'll pair 2 with 8 and 5. 2 with 8 and 5. and then I'll also pair this thing. 2 is there, and 3. 3 I'll pair 4 and 7. Okay, now can you cover these in like 3 elements? Arjun, can you cover these in 3 elements? Like 3 elements, you will need 1, 2, 3, 4. These 4 only covering, you'll need 3 elements. You can't do this in 3 elements, right? For example, if you choose 1, 4, 5, you can't. If you choose 1 and okay, 1, you have done this. Now 4, 5, 6, one of those you have to choose. Suppose you choose 1, 4 and 3, let's say. 1, 4 and 3, you still have this left. Yeah. I think this works. Color 7, 5 and 3. 7, 5, 3, 7, 5, 3, 7, 5, 3, 7, 5, 3. Okay, don't worry. 7, 5, 3 of colored. I'll just add 1 and 1, 4 and 6 here. Now you tell me. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 sets from 8 subsets of 1 to 8. And yeah, now what do you want to color? Just tell me. Color 4, 5, 1. Color 4, 5, 1. 4, 5, 1. 4, 5, 1. 4, 5, 1. Okay, 4, 5, 1 does this. So 4, 5, 1 will do if I have 1 or 4 anything. So I can't have 1 or 4 here. And previously you had 7, 5, 3. So 3, 5, 7 I can't have. 4 and 1 I can't have. So I need 2, 6, 8. So let's do 2, 6, 8. Now if this is also done, then this previous construction will not work. Suppose I choose, okay, what if you choose 2, 6, 8 here? Okay, this doesn't work. 2, 6, 8 doesn't work. If you choose 2, 5 and 8, 2, 5, 8 also doesn't work. Okay, this shouldn't work, yeah? Arjun? Other people can also try. So this seems to be the construction. 8, 4, 1. 8, 4, 1. 8, 4, 8, 4. 8, 4, 1. 8, 4, 1. 8, 4. Yeah, 8, 4, 1 works. Cool. 8, 4, 1 also works. So maybe n by 3 works. I don't know. Maybe n by 3 works. Then give me a proof that n by 3 works. Like try a proof. It will be very nice if you reduce the bound from 2n by 3 to n by 3. Because 2n by 3 I have a proof with me. Like which is like not really difficult. It's quite easy. But yeah, actually the people are watching this to learn right now, and you guys also want to learn. So let's just prove 2n by 3 for now, and I'll surely get back to trying this n by 3. I'll either find a counter example or I'll try to prove this. That's for sure. Okay, Arjun, I'll get back to you. Cool. And right now, if you have a proof of n by 3, then please share it. Probably you don't. You have guessed n by 3, right? You have guessed that n by 3 works. I think for small cases it works. I'll try to write some programs to see if this works. I'll try to do some programming and see if it works. If it actually works, then I'll try to prove it. If it doesn't, then I'll give you a counter example. Yeah, you guessed through small cases, but the thing with big cases is that in small cases n by 3 plus 1 and 2n by 3 is almost similar. So probably this still works. Like 2n by 3 is obviously not strict. I am saying in 2n by 3 I can do, but the fact that you can actually reduce it to n by 3 seems too much to me. So I think probably we'll have to reduce it to like something like I don't know. We have to try for n big, and for n big, writing down by hand is too difficult. So I have to figure out a way to write a program for this, and I'll try my best. Try my best. For now, let's just prove it for 2n by 3. Okay. let's get back to our problem and try to prove it. Ashish says, is my approach fine? I didn't see your approach, Ashish. Please repeat it. I was trying to disprove n by 3, but I haven't been able to. So yeah. And now again they say I can't hear anything yeah, on YouTube, which is sad. But we'll see. Let T be a member of 1 to n with most appearances in AI. If we decide to color T, I think we need to calculate a lower bound on the number of T times T appears in AI. So, okay. So, people, I think this greedy algorithm should work. Yeah, in VisIQ, my video is not on. But can you hear me on YouTube? That's the thing, Arjun. Okay. So, let's try the approach Ashir is saying. Ashir is saying our greedy algorithm is will pick. We have to color some elements, right? We have to color 2n by 3 elements. We have to color 2n. Oh my god, this problem started now. Really? Change color. Apparently, changing color works or what? Change color. Where is change color thing? Here? No, here. Okay. Yeah. So we what Ashir is saying is that basically when we have 1 to n, right? And we have 1 to n, and we will pick that element which has maximum appearances among a1, a2, and so on. So we have the elements 1 to n, and we have the sets a1, a2, and so on up to an. Now, a basic greedy algorithm is what? You want to choose colors. You want to color those elements which appears in a lot of places, right? That's what you are doing when you are trying to color this. When I was trying to disprove this n by 3, what were you doing? Instinctively, what you are going for is the element which appears in a lot of sets, right, Arjun? Yes. So that's what we will do, and we'll see that this will prove our 2n by 3 bound. Okay. So what we'll do is at each step we'll pick t, because Ashir wanted to be t, such that t appears in the most number of sets. Right. Now, so we have to show that we can only do this 2n by 3 times. Like after we have done this 2n by 3 times, every set is empty. So what we'll actually do is when we pick an element t, we the sets which contain t, we throw those sets out, because those sets we have already dealt with, right? We already have one element colored which is in that set, right? So when we throw that element out, we want to say that after 2n by 3 steps, there will be no set left. Okay. Now what will happen? Initially, when you will pick an element, there will be one or two or three sets. Like there will be three sets, for example, let's say, which will have that. Then you'll throw them out. Arjun, we are trying to prove that we can color 2n by 3 elements among 1 to n, such that every set has one element from among that from the colored elements, right? So for that, what we are doing is we are seeing which element occurs the maximum number of times among a1, a2, a3 dot 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 an. The element whichever appears the maximum number of times, we are choosing that and we are coloring that. Once we have colored that, we have already dealt with the sets which contain that element. So we throw those sets out and we look at the remaining sets. Okay? Now, what will happen? So, and I am saying that you can at most do this 2n by 3 times. And if you do this at most 2n by 3 times, then by 2n by 3 times, there are no sets left. Okay? Like all the sets have at least one element colored. But how do you prove that this 2n by 3? Okay, let's say that after k steps, you get everything disjoint. What does that mean? That after k steps, all the sets that are left, suppose say a4 is still left and dot 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 maybe an is also left, okay? And so all of these become disjoint in the sense that if you pick any element now, it only belongs to that set. Okay, so till the time you are not getting disjoint sets, all the elements that you are picking, they had to be in at least one set, right? At least two sets. At least one set is obvious, yeah. So does that give us a bound on k? There are n elements in total, right? And each time we were yeah. So why is what are you guys saying? K less than equal to n by 3. Why is that true? No, because the element is in at least two sets. That's what I said. K after k, everything is disjoint, right? So k is actually less than equal n by 2 because any element that we are picking from the first step till the kth step is in at least two sets among a1 to an, and so k has to be less than equal to n by 2. Now, when you have picked out k elements, right? When you have picked out k elements, there are n minus k elements remaining in this set, right? And all of these a4 to an are disjoint, right? And all of these are disjoint, and the size of all ai is 3. So some sets which are disjoint has size 3, and there are n minus k of these. So how many steps? So how many more steps can you do? The remaining number of steps, how many will that be? The remaining number of steps, let's call that r, that will be less than equal to, actually that will be exactly equal to n minus k over 3. Because right now everything is disjoint, you have to pick all the elements that are in those sets. So that will be exactly equal to n minus k by 3. So the total number of steps is just n minus k by 3 plus k, which is n by 3 plus 2k by 3, and k by 3 is k is less than equal to n by 2. So this is less than equal to n by 2 plus n by 3 plus n by 3, which is 2n by 3. Okay. Now the number of steps is obviously an integer. It's less than equal to 2n by 3. So it's also less than equal to floor of 2n by 3. The number of steps. And we are done. Does everybody see this? Okay. I mean, it doesn't matter. At the end, we just want it to be less than equal to the 2n by 3. So if you want to bound it by boxes, it's fine. But in the end, also we can just put the box to get that. Yeah, it's less than equal to, I'm saying, right? Anyways, so let's continue with the problem 3. Problem 3 is an IMO shortlist problem. It asks you. Okay, you just read this problem. It's like it's apparent what it asks. So guys, read the problem. Try it for 1 minute, and then I'll show you the solution. Okay, so let me try to explain the problem to you. After that, I'll give you some more time. So, what does the problem say? The problem says that basically the sets of the form, if this is the number line, sum x, okay, x plus a and x plus a plus b, or the sets of the form x, some x plus b will be here and x plus a plus b, are called historic sets. Okay, so the distance between this is a and this is b, these three elements, this is x, this is y, this is. So let me just try to explain the problem to you. If this is x, this is y, and this is z, then this distance is a and this is b, or this distance is b and this is a. The y could be here too. Okay? Right? Guys, can you hear me? Is there a problem with hearing again? Okay, so what do we want? We want to show that all the integers, if we have all the integers from 1 to n, we can cover it using these sets. These sets are called historic because I don't know, this was the A and B were chosen to be something 2001 and 1917 something in America's independence year. I don't know what it was, but they chose that, and this IMO was held in America and something like, some history it has. I don't know. But anyways, these are called historic sets for whatever reason, and we want to show that we can cover this. Now, what would be the greedy approach to this? The greedy approach will be like you go on covering, right? First, you choose 1 and 1 plus a and 1 plus a plus b. Then you choose the next element and go on like this. But if you do this, what's the problem? What will be the problem if you just go on do this, go on doing this? You will face a problem when suppose you have some element here and you want to color it. I mean, you want to put that in a historic set. This is some element x, but either x plus a or x plus b is already has been chosen by some other historic set, or x plus a plus b has been chosen by some other historic set. But if you just simply, at each step, if you just simply pick the smallest element which has not been chosen yet, then x plus a plus b will always be available, right? So that's done. So you can just, this is the greedy step. You just choose the smallest x at all possible stages, right? But still, you may have that x plus a and x plus b are both covered. At that time, you won't be able to choose a y. So what do you do there? For that, what you do is, and the greedy step is this. Okay, let's just think about it. When are we facing a problem? We are facing a problem if some lower elements are left out, if some small elements are left out. So small elements are bad in some are good in some sense, right? I mean, they are bad, so we need to cover them first. So always pick small elements over the larger elements. That should be our logic. Okay? So we'll always prefer x plus a to x plus b. If x plus a is empty, then always choose x plus a over x plus b. Okay? So this is our algorithm. The algorithm is pick the smallest element which has not been picked yet, which has not been picked till now. Let this be x. If x plus a has already been picked, then pick x plus b. If not, then just pick x plus a. Okay? And if, as we are speaking the smallest, x plus a plus b will always be available. Now we just need to show that x plus, we will always be able to pick x plus a or x plus b. Suppose this fails, suppose we can't do that, okay? Yeah, your approaches are the same, but you still need to prove that this works. This actually works, but we need to prove this. How do we prove that? We say, okay, suppose this doesn't work, this stops at some time, this algorithm. What does that mean? That means there is some x plus a, x is the smallest that we haven't chosen yet. Then x plus a plus b has to be free, because by the smallest assumption. So that is also free. That means one of x plus a and one of x or x plus b is not free, right? If x plus a was free, then we would have chosen that. We are not able to choose either x plus a or x plus b. That means both of these are already taken. But what does that mean? That means if x plus b has been taken, x plus b has to be the largest element in its historic set, right? X plus b has to be the largest element in its historic set, which means this x plus b minus b minus a minus b plus a, which is basically x minus a, this element x plus b and some other element are in the set, but x minus a plus a is x, right? So why did you pick x minus a plus b, which was somewhere here? We always want to pick the smallest element. So when we had a choice, when we picked x minus a, we should have picked x. And this is something that our greedy algorithm will never do. Pick this next one, right? So that's a contradiction, and so this can never occur. So this algorithm will go on forever, and it will go on picking the smallest element, and in this way it will cover everything. So hence we have proved that the positive integers can be partitioned into these historic sets. Okay? Does everybody get the solution? Let's try problem 4 now, okay? Let's try problem 4. Problem 4 is like IMO, which was held in South Africa. So I think it should be IMO 2014. It was either problem 2 or problem 5. I don't remember which, but it was one of those. So yeah, it is problem 2-5 difficulty, but it's not that difficult. You'll see. If you're just greedy, see, these are some coins, right? So you want coins. You be greedy, and this will work out. Is my method correct? What was your method? I have to see actually, Arjun. I think you can consider sets of the front 3k, 3k plus 1, 3k plus 4, 3k plus 2, 3k plus 3, 3k plus 5, and then 1. Then you are done. What do you mean you are done? A and B are given to you. You don't choose A and B out of your like whatever you want. A and B are given to you. A, B are given, where A and B are positive integers with A less than B. Are, maybe I should add given here. Like A or B and some fixed things. Whatever A, B are, yeah, A, B are constants. You don't choose A and B whatever you want. For any A and B, this is true. So like the proper way to frame this is for all A, for all B, this is true. But anyways, let's try problem 4. So what does problem 4 say? Problem 4 says that there is this bank in Cape Town which has coins only of the form 1 by n. Okay? Yeah, I'll give you time. I'm just explaining the problem right now. So the coins are all of the form of denomination 1 by n for some positive integer n. And uh, given a finite collection of such coins with total value at most 99 plus half, prove that it's possible to split this collection into 100 or fewer groups such that each group has total value at least at most 1. So the first thing that you realize after seeing this problem is probably 100 is not something unique, right? So if you choose any n instead of 100 and n minus half instead of 99.5, you should be okay. Because like 100 is, I mean, 10 is a arbitrary number that humans picked because they had 10 fingers on the hand, and 100 is a square, so it's a nice number. They have put 100 there. You should be able to realize with experience that this 100 is nothing special. So let's get that out of the way. So we'll prove this for n and n minus half. N minus half. Okay? Now, suppose we have two coins of say denomination 1 by 4, right? Then we can just combine them to a coin of 1 by 2, right? And if in this combined version we can do, then in the original also we can do, right? So basically, if we can combine some coins, if we have say, if we can combine any two, any three, any combination of coins, we'll combine them, okay? So for example, if we have 5 coins of 1 by 5, we'll just combine them to make one coin. Yeah, here's the problem. Okay, so if we can combine any coins, we'll combine them, right? Now, one thing you will be able to notice is that the coins which are of, now suppose we have split all the coins into groups and we are left with very light coins, light in the sense very small value coins, okay? Now small value coins you will always be able to put. Why is that true? Because the average value, however you have split, however you have divided into groups, okay, the average value of each group will be at most n minus half by n, right? So that is 1 minus 1 by 2n. So there will be always at least one pile, there will be at least always one pile which will have value less than equal to 1 minus 1 by 2n. So the coins which are of denomination greater than 1 by 2n, at the end you can always add this to this pile. Cool? So what I'm trying to say is, we are given what? We are given weight at most n minus half coins. We have to split them into groups. Each group has weight less than equal to 1, and we have to split them into n groups. Right? So what I'm saying is that, firstly, if you can combine any group of coins to get a to get a larger weight coin, which is also eligible in the sense which is also like of the form 1 by n, right? So in the sense that 1 by 4 and 1 by 4 you can combine. In general, any 1 by 2n, any two even coins you can combine to make a smaller odd coin. Okay? So if you have such things, you just combine them. That's one greedy step. The second thing that we are doing is, once we have divided the coins with larger weights into say n groups, right? The coins which have small weights, like which have weights smaller than 1 by 2n, these can always go into some group, because the total weight is n minus half. So the average weight is n minus half by n, which is n 1 minus 1 by 2n. And so there will be at least one pile or one box which has weight less than equal to this. And so you can put this coin there. You can put this coin there without increasing the weight more than 1, right? So right now we can forget about all the coins which have weight less than equal to 1 by 2n. So we only have coins of weights from 1 by 1, 1 by 2 and so on up to 1 by 2n minus 1, right? And we can have many coins also, but all notice that all the even number of coins, they will be only 1, because if you have two coins with this 1 by even number weight, right? If you have two coins of 1 by k weight, both of which are even, then you can just add 1 by 2k and 1 by 2k and get 1 by k, right? So right now we want to group these into things. So 1 by 1 till 1 by 2n minus 1, we want to put them into n groups of less than equal to 1. Notice that even for odd coins, suppose 2k coins of 1 by odd weight, for example, coins of weight 2k 1 by 2k minus 1, 2k plus 1, there can be at most 2k of these, right? For example, coins of weight 1 by 5, you can have at most 4 of these, because if you have weight 1, you can just put it away, right? So weight 1, you put it away. 1 by 2 and whatever coins you have of 1 by 3, you put them in one pile. Okay, no, sorry. 1 by 2 you put in one pile. First pile you put only 1 by 2 coins. Second pile you put 1 by 2, 1 by 3 plus 1 by 4. Now 1 by 4 there can be at most one coin. 1 by 3 there can be at most two coins. So this weight will be less than equal to 2 by 3 plus 1 by 4. Okay? And what is 2 by 3 plus 1 by 4? It's less than equal to 1. Cool? So this is what we'll always do. For we'll put 1 by 2k plus 1 or 2k minus 1 plus 1 by 2k coins in the kth pile. And this will work because each of those things, 1 by 2k plus 1, there will be at most 2k of those, 2k by 2k plus 1 and plus 1 by 2k plus 2. Yeah, so this is always less than equal to 1. And then at the end, whatever is bigger than 1 by 2n, we put that into another pile. Cool? You put that into whatever pile has less weight. And there will be at least one by this n minus half by n logic. So this works. Should I repeat it or did you guys get it? Because I was probably not that clear. So let me just tell this proof in a way that you'll write in a solution. Before, what I told is how you can get to this idea. When you'll write this, you'll write this in the following way. You will write, okay, firstly, if you have any coins of weight 1, you can just throw that away and induct down. Okay? 1 coins don't matter because we want to prove n plus half, n minus half can be divided into n piles of weight of each pile weight less than equal to 1. If you have a coin of weight 1, you can just put it in one pile and induct downwards. Okay? You can get it from n minus 1. So by induction, there is nothing of weight 1. Okay. Secondly, what you will do is, if you can combine, then combine and induct downwards, because then the number of coins decreases and you can induct downwards. Okay. So if you can combine. When you have combined the coins of the form 1 by 2k, there will be at most one of these, and the coins of the form 1 by 2k minus 1, there will be at most k of these. Right? Now we are left with coins of the form 1 by 2 to 1 by 2 n minus 1. So for example, if n is let's say 3, then we'll have 1 by 2, 1 by 3 and so on up to 1 by 23 minus 1 is 1 by 5. So half will put in one pile. Next pile will put whatever coins of half we have will put in one pile. Next pile will put 1 by 3 and 1 by 4s. And next pile will put, okay, this seems strange because n was 3. Okay, there's some end case probably I have uh, made a mistake or something. Some end case. Because, okay, no, 2 by 3 plus 1 by 4 is less than 1. That's not a problem. And then what you have? Oh, okay, no, it's not a mistake. It's fine. Yeah. So here you'll have 4 by 5 or whatever. So these two piles are done. But there were supposed to be 3 piles, right? There were supposed to be 3 piles. Let me check the problem statement again. Yeah, guys, can you not hear me? Can you hear me or not? Okay, cool. Yeah, so there's probably some end case that I'm missing here. Just check whether it will be 2k plus 1 or 2k minus 1. But the basic idea is this, that whatever small coins you have, you can put them at the end by this weight by average weight less than equal to average weight logic. And whatever even coins you will have, you will have at most one of those. So one of even coins and at most 2k minus 2 divided by 2k minus 1 of odd coins, because like at most 2k minus 2 of odd coins are there. Otherwise you can just combine them to coins of weight 1 and you put them into piles. And so 1 by 2n less than equal to 1 by 2n, you can put them at the end. And other than those, there are approximately 2n type of coins. Two of those consecutives you group into one and they will have weight less than equal to 1, and that will work out. Okay, cool. If that's fine, I'll just end the class here. Thank you for attending. People on YouTube, thank you for watching, and I'll end it. Bye. Yeah. And okay, by the way, information for the people in Superstars. I think you have a test today and tomorrow, and this test will be yeah, okay. If people have left, I can do nothing, but you can say this in the group or whatever, that there will be two problems from greedy algorithm and extremal principle. So this is like a hint for you. So you try to use greedy algorithm and extremal principle in the problems that you get, in the non-geometry problems that you get. Okay, there will be some geometry problems. Other than geometry problems, whatever is there, you try to use greedy algorithm and extremal principle there. Okay, cool. Bye. Guys on YouTube, this is actually live, but the thing is, I can't read your chat because I have to read the classes chat. But yeah, thank you for attending.